Hey guys, Buildzoid here from Actually Hardcore Overclocking, and today we're going to be taking a look at yet another RTX 2080 Ti custom PCB. Though admittedly, I think I've done most of them on my own channel, so not that fitting, but I've done a lot of these at this point. So I think this is the only custom card I haven't done yet. So this is of course the EVGA FTW3. And personally, for me, the highlight feature here is that this has a BIOS switch.
Before that, this video is brought to you by Corsair's Vengeance RGB memory. Corsair's Vengeance RGB RAM uses pre-screened ICs for better overclocking headroom and tighter timings. Corsair's RAM also has the benefit of wide-reaching motherboard support by landing on qualified vendor lists for motherboard makers, ensuring wide compatibility between boards. Learn more at the link in the description below.
Ultimately, I'm not sure how useful it's going to be because you can't mod the BIOS on NVIDIA cards, but you can, experiment with using other card, trying to use the BIOS off of a different card to try get the power limit or something. But ultimately, all of the BIOSes are going to be more or less the same because all of the BIOSes need to be approved by NVIDIA. And from what I've heard, NVIDIA is pretty awful about approving BIOSes that do cool stuff. So yeah, but it is a neat feature, and it is nice that you do have the option, even though unfortunately is probably not going to be all that useful to most people. Now then, let's get on to probably the more interesting part, the VRMs. VCore VRM is the pretty standard layout for a RTX 2080 Ti, where you have one group of phases on this side. So that's one group of VCore. And then you have the other group of VCore over here. So that's also VCore. And above the larger of the two VCore groups, we of course have the memory power, so VMem. VMem is for powering all of the... I don't know why I can't write an M. Is for powering all of the GDDR6 memory chips around the GPU core. Then we have a bunch of minor voltage regulators that I'm not even going to try to point out on this card because they're kind of all over the place and they're really hard to identify. But the card does ultimately need sort of the following voltages. It needs a PEX rail, and that's quite possibly generated by this or this. Or it could be some other thing that I'm not even noticing on the card. But that powers the PCIe interface as well as some internal PLLs of the GPU core. Then there's a 1.8 volts rail, which powers the BIOS chips that NVIDIA uses, as well as the VPP rail of the GDDR6 memory chips. So that's a supporting voltage for those to function. It doesn't really do a whole lot. If overclocking-wise, it doesn't actually do anything. Then we have also a USB-C rail because all of the 2080 Ti's have a USB-C port, so you need a power supply for that because you don't get 5 volts for your USB port from the PCIe slot. And because you really don't want to have the VRM powering the VRM, there's a VRM for the VRM, probably since you don't want that one going down when somebody messes with the USB port, there's also a separate 5 volts voltage regulator located somewhere on the card, probably in this area, though this is that's an input filter, that's probably an input filter, that's an input filter. This could be 5 volts. This also could be 5 volts. I assume this is more filtering. So yeah, really hard to really hard to identify these minor rails with just pictures of the card. So that's the best I can do there, but they do exist. They're scattered around the card. They're not really all that important. Now then, I guess let's get into the important VRMs, starting with the VCore. So the VCore here, of course, looks like a 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 phase. The issue is that for some reason, and I assume it has to do with transient response requirements, but basically all of the RTX 2080 Ti's ultimately don't use any doublers. And instead what they're doing is what I called ASUS out on the Maximus 11 Hero, where what they're doing is essentially they take one PWM signal from the voltage controller and shove it into two phases at the same time. which is why you have so many power stages and inductors when the UP9512 voltage controller located on the back of the card. We're not actually going to go there because we can go on the back of the card. It's just a bit blurry. Oops, I've put too many divisions on that side. But the UP9512 that this card uses is ultimately an 8-phase voltage controller. So that's this chip right over here. And in fact, because EVGA has a nice and tidy PCB here, we can actually very clearly see the current monitoring circuits, which you'll notice are 1, 2, 3, 4, 5, 6, 7, 8. I mean, clearly, we can blurrily see them. But yeah, these are the current monitoring circuits. And so basically, as far as this chip is concerned, the VRM is an 8-phase. And as far as the PWM signals go, it's also an 8-phase because there's no doublers to shift the PWM signals out of phase. So ultimately, you have 2 power stages turning on at the same time, and therefore they're in phase with each other. There's no sense calling them separate phases when they turn on at the same time. And this is actually what's going on with most of the RTX 2080 Ti's. Now, there is a couple cards which do have 10-phase voltage controllers with 10 current monitoring circuits, and you can actually see that on them. So those definitely have 10 phases, but those are also wired to look like 16. Those also look like they're 16 phase or some higher phase count. But ultimately, all of the 2080 Ti's are running either 8 or 10 phases. And the reason that these cards don't use doublers, because we can kind of see that, like on this side of the card, we have our six inductors and power stages. Here we have the other 10 located on this side. Well, we can see on the back of the card, we can actually see footprints for what are probably doubler chips, because there's 3 of those. One more down here and another one down here. They're conveniently within the sort of distance of the power stages. And then on the other side of the card, we have this one right here, and this one, and this one. So we can clearly see that somewhere along the line, somebody wanted to use doublers, and then they went like, okay, no, we can't use them for some design reason. I'm assuming it's going to be due to transient response, because that's really the only thing that doublers affect heavily. Well, relatively heavily. You can try design around it, and ultimately GPUs are probably much more sensitive to this than CPUs, which is why it seems that NVIDIA is probably requiring that people just don't use doublers. Otherwise, I'm pretty sure a bunch of board partners would, because if you look at high-end 1080 Ti's, there's doublers freaking everywhere. But with the 2080 Ti's, nobody's using any doublers, because basically when you use a doubler, there's a couple nanoseconds of delay added to your PWM signals. And if you're just trying to match the output voltage of the VRM relative to the current pull of the GPU core, and you have a GPU core as large as a, TU102, pulling, limited to 200 and the thing is, NVIDIA gets most of their power efficiency not from the actual manufacturing process itself, but from really aggressive power gating. So the end result is that, yes, this GPU has an average power consumption of something below 300 watts. I can't remember what exactly it was, but the peak and minimum power consumption that the card will pull are going to be massive relative to way off from the average power consumption, which means the VRM has a lot of work to do in terms of transient response, because your current draw is anything but consistent. And for that reason, eliminating the doublers makes kind of a lot of sense from a design perspective for the RTX 2080, for the RTX 20 series of GPUs. Because that is kind of like everybody's doing it. Even the Galax Hall of Fame card, which was $1,800, doesn't have doublers. So that's the only reason I can think of that is you don't want to use doublers. Now, doublers do have some benefits. They can improve your VRM efficiency because they can give you the ability to properly current balance all of your phases instead of just trying to rely on the fact that as power MOSFETs get hotter, they go higher resistance. So like if this chip gets, if this chip is pushing more current, it's going to be producing more heat. Over time, it's going to get hot enough that the internal, like the resistance of this chip is going to be high enough that it's going to push more current into the chip that it's in parallel with, because these two will probably be sharing a PWM signal. So it'll kind of self-current balance, but it's not going to be optimal. And also with doublers, you would have slightly improved, slightly improved. You'd have improved input and output ripple. The thing is, once you have 8 phases, trying to go even higher on the phase count, generally, like, there's diminishing returns. So going from 8 phases to 16, the input ripple and the output ripple probably wouldn't change a whole lot. So there's nothing really wrong with this being an 8 phase, but it's definitely not a 16. And my statement about the Founders Edition in the past being a 13 phase is just straight up wrong. That's also an 8 phase. And in fact, most of the 20 series is either on 8 or 10 phases. Now then, so that's kind of that's part of the control scheme phase-wise. The UP9512 also introduces a 2 megahertz maximum switching frequency, which we cannot access. Well, actually, we could if we had a full data sheet for the chip, because I have recently gotten my hands on the pinout for this thing, and it is actually very easy to vault mod, and it should be possible to actually physically set your modify the load line with a resistor on the GPU. So that's pretty cool. That should be modifiable with a hard mod as well. Switching frequency is actually also set with a resistor. However, that resistor also sets the address of the chip on the on the SM bus interface, which is also like, it's similar to I2C, which you can actually use I2C as well for that. But so ultimately you can't, like, while, if you had the data sheet, it would just be a matter of replacing one resistor on the card, and you could change the switching frequency to whatever you want, which would potentially, like, the reason why you'd want to do that is if you crank up your VRM switching frequency, you can actually reduce your VRM output ripple at the cost of more more heat dissipation, because you're switching your MOSFETs on and off more often in the power stages, so the power stages produce more heat, the VRM gets less efficient, but you get better output regulation. So that's kind of how that works. It's a fun fact. VRM efficiency and VRM output regulation generally don't go hand in hand with each other. Like, they're not necessarily linked to each other. But anyway, this does go up to 2 megahertz, and it is still on the PWM vid interface, which is the reason why it is so very easy to hard mod this thing. So yeah, that's the UP9512, and it's basically a bunch of bolt-on upgrades over a UP9511. In fact, the pinout for this thing is super similar to the UP9511, which is also why it's so easy to, why it should be relatively easy to modify. Now then, for the actual power stages on this card, we are looking at the ever so popular FDMF3170s. These are pretty much the default power stage for an RTX 20 series GPU. Everybody uses them. Well, not everybody. Asus likes to use their more expensive Texas Instruments parts, but these are relatively cheap. They are very powerful. They do push 70 amps. They are also, I forgot to mention, these are smart power stages, not just any power stages. And the reason why these are called smart power stages is because they integrate current monitoring and temperature monitoring, and actually a really... like, they also integrate protections like 140 degrees Celsius, and I'm doing that wrong again. That does... Nah, this looks better to me. I'm just going to do it that way. I don't care which way is the correct way at this point. But 140 degrees Celsius over temperature protection and 80 amps over current protection, so they won't allow you to actually, like, overload them. Now, the cool thing is, since there's so many power stages here, also, this is one of those things where if that 80 amp OCP kicks in, it'll force the current onto the other power stage in the pair of two. So it'll kind of, like, if you were maxing out your current capability, then they would actually current balance themselves, kind of just bouncing off of the OCP there. Though if they bounce off that enough, it'll eventually raise a flag with the controller, and the controller will probably just shut down the VRM at that point. So it's not like you can overload this forever. But ultimately, since that trip point is so very high and there are so many phases, you're never actually going to hit that. Like, there's no way you're actually going to hit that under normal applications unless you try to well, I guess if you wanted to make like a low voltage room heater with this VRM, yeah, you could probably hit the OCP if you were working on doing something like that. But while powering the TU102 core, that core is going to die before the voltage is high enough to push that amount of current. Now then, the end result of all of these lovely power stages and having this many of them in the VRM is that the efficiency on this thing is pretty epic. So it's not the most efficient though. The Texas Instruments parts are slightly more efficient. I think Infineon also has power stages that are slightly more efficient. They're all rated as 70 amp parts. But yeah, some of the competition has slightly better parts. They're also way more expensive. But ultimately, efficiency-wise, what we're looking at here for a VRM switching frequency of 500 kilohertz and a output voltages of 1.8 volts and 1.2 volts, which I've finally gotten my hands on a data sheet for a proper data sheet for a 70 amp power stage. So instead of scaling this off of like a previous generation 60 amp power stage, which is what I did in the past, this is actually scaled off of a comparable kind of part. So this is now more accurate than in the past. And I think in the past it was actually a bit low compared to what it's going to be now. So anyway, this is what the data sheet of the FDM-F3170 itself is spec'd for. I can't tell you what I'm scaling this according to because that data sheet is NDA'd. Now then, it runs off of 5 volts only. So I'm not going to mention the drive voltage here. So then, for the stock current level of around, like, we're not, like, it's not actually going to run stock at 200 amps. It's going to run probably a little bit more than that, but around 200 amps output, 1.8 volts or 1.2 volts, you're going to be looking at 1.2 volts about 20 watts of heat, and 1.2 volts at about 17 watts of heat. Honestly, with this many phases, you could probably, unfortunately, the thing about all power, smart power stages and really any kind of power stage is that everything has an efficiency curve that looks like this. When you have 16 of them, you tend to be in this area at the lower currents. Now, as you go higher current, the efficiency starts getting better for the VRM, but your overall efficiency of the GPU is going to be lower because it's going to be pulling a ton more power and not producing a whole lot more FPS. So, just kind of it's going to be pulling disproportionately more power than it's going to be producing FPS, right? Like you could get like a 20. Well, I don't remember how much these overclock by, but let's say you get a 10% performance increase. Well, you're probably going to see more like 20 or 40% power consumption increase for that kind of performance increase. But ultimately, the VRM is actually going to be running a bit more efficiently at the higher current outputs. Now, for overclocking on sort of water cooling, you're probably going to max out somewhere around the 300 amp range, maybe a little bit above that. At that point, the VRM at 1.8 volts would be producing about 30 watts of heat. And at 1.2 volts, it would be producing more like 26. Now, as we keep going up in current for, at this point, I'm going to say like sub-ambient, so probably around dry ice levels, you might be looking at something like 400 amps of current pull. And at that point, 1.8 volts would be producing about 45 watts of heat, and 1.2 volts will be producing about 39 watts of heat. And the great thing is, even at this point, you probably would just you would probably get away with just a gentle breeze over the VRM without even needing a heatsink on it to keep it from overheating, because that 39 watts is spread across a lot of parts, right? Like that is spread across all of these power stages, and they're not even like in one big group right next to each other. So ultimately, the thermals on this thing are just like this VRM. If you're on like water cooling, you could totally, if you want to water cool the card and you can't get like a full cover block, then it would be totally a valid thing to do to get one of those GPU core only water blocks. You'd be fine because the VRM is going to be completely fine. Though the VRAM, on the other hand, that might have a bit of an issue, but The VRM itself is not going to have a problem with a sort of almost zero airflow environment because it's just so massive overkill for the lower current outputs here. But it is worth noting that at this point, it is very much like in the peak part of the efficiency curve. So that's kind of why the Founders Edition, it has a 13 phase. It nails the peak of the efficiency curve at stock settings. So yeah, that's kind of the reasoning behind why a lot of the 2080 Ti's are so ridiculous in the VRM department. Now then, moving on from dry ice to more like liquid nitrogen, we hit sort of 500 amps and possibly even 600 amps. And, you know, off the deep end, like, just in case, we're also going to look at what would happen if you tried to push 700 amps. Though I don't think that you'd ever actually hit this. A completely maxed out 1080 Ti on LN2 would be somewhere between the 400 and 500 amp range. I'm assuming a completely maxed out 2080 Ti will be somewhere between, and I just screwed up my paintbrush, which is great. Will be somewhere in between that 500 to 600 amp range. So, yeah, this is just kind of like a theoretical consideration. And really, even this is mostly theoretical because how many people are ever going to run liquid nitrogen on one of these? Now, for that 500 amp range at 1.8 volts, you'd be probably looking at about 60 watts of heat of VRM heat output. So at that point, you might need more than a gentle breeze over the power over the phases. And at 1.2 volts, it'll be producing about 52 watts. And yeah, like at that point, airflow would be a good idea. 600 amps, you're going to be looking at more like 82 watts of heat, which, yeah, you're going to need airflow. Maybe even heat sinks, but probably just airflow, assuming you have a high enough RPM fan. Ultimately, it is worth considering that in extreme overclocking, the VRM is fine as long as the benchmark finishes before the VRM overheats. So you don't even need to have good enough cooling. Like, you don't need to be able to run the VRM at like 600 amps for an hour. It needs to last for like 5 minutes before it overheats. If it can do that, you're good. So even here, you could probably get away without heat sinks. And it's also worth noting that the liquid nitrogen has a tendency to freeze everything around the GPU core. So if the VRM is sitting idle, like if you're just sitting idle on desktop for long enough, over time, the IO section of the GPU will like freeze over, and so will the, like everything really, all the way down to the PCIe slot and through the motherboard. And yeah, the longer you run for and the more time you spend sitting idle on desktop, the more frozen everything's going to get over time. So, yeah, like the VRM cooling considerations on LN2 are very different from like normal use case scenarios. Now, 600 amps, 1.2 volts, you'd be looking more like 70 watts of heat. And the airflow thing still applies. Like, this is a lot of heat at this point. And 700 amps output, you're going to be looking at about 106 watts for our 1.8 volts and about 92 watts for 1.2 volts. So yeah, at that point, it's going to be pretty, like, that's a lot of heat. But it's also worth noting that, you know, at 1.8 volts output, 700 amps, you're going to be looking at close to like 1.4 kilowatts of power, right? Like 1,400 watts coming out of the VRM, and the VRM is only going to be producing about 106 watts of heat, which is still pretty good efficiency, right? So yeah, that's worth considering. But at that point, yeah, you will need VRM cooling, though, of course, this is even on LN2, I don't think you're necessarily going to hit that. So the V-Core VRM, in sort of standard RTX 2080 Ti custom PCB design fashion, is complete and ridiculous overkill for what most people are probably going to use it on, which is going to be somewhere in this range. But yeah, it's nice to know that, you know, there's no chance of you ever overloading the VRM on this thing. And these do come with a lot of safety features that include functionality to like save the GPU core if the high side MOSFET or something fails. So even if one of these breaks, you're probably going to be fine with the VRM. Like, the VRM is still going to be relatively functional, which is a really neat feature of these smart power stages. Now then, for the memory VRM, we're looking at similar levels of ridiculous overkill, and actually the memory VRM is like very much kind of you know, it's in that part of the efficiency curve where it's like you could probably get away with less phases and not have any issues. But the memory VRM is a actual 3-phase. You can't, you know, do anything weird about that. The voltage controller for that is also another UP9512, except this time it's running in, that is not 9512. That's another UP9512 right there. That's running in 3-phase mode. And same as what I said for the one on the back, this one on the front is going to be very easy to mod, just because it's the same chip. So if you want to mod your memory voltage, that's great news, isn't it? Though, admittedly, like, that's probably a great way to kill all of your GDDR6, just because GDDR5X also already wasn't exactly tolerant of high voltages either. So, yeah, also, the voltage applied to the memory chips is also slightly applied to the GPU core, so you could also break the memory controller. So, again, not the best idea to mess with that for daily usage. Now then, since this is the sort of bog standard 3-phase memory power that we've seen on every single RTX 2080 Ti, using the exact same power stages as every other RTX 2080 Ti, this also has the same exact efficiency, where it does 20 amps, and we're again talking about these operating parameters. 20 amps output, well, except for the part that we're only doing 1.8 volts, because scaling down to 1.2 volts doesn't work at this kind of low current output level. 20 amps output, you're going to be looking at about 2 watts of heat, this is below what I think as far as I'm aware, the GDDR6 memory chips should be pulling, or it might be, yeah, that might be a bit low. I think they're pulling more like 30 amps, and at that point, the VRM will be producing about 3 watts of heat, and at 40 amps output, the VRM will be producing about 3.5 watts of heat. So yeah, this absolutely does not need any cooling whatsoever. This is ridiculous overkill, but that's standard for these RTX 2080 Ti's. Anything else I'm missing? Oh yeah, we have a whole bunch of circuitry on here for current monitoring and current balancing. Kind of an interesting difference between this card and a lot of the other cards is that EVGA actually has an INA3221 somewhere on here. Which is kind of, and that's different because normally all we see on 2080 Ti's and really any 20 series cards is the on semiconductor NCP 45491 current monitors, and those basically take care of all your shunt resistors. So that's what's monitoring those. There's also, I think there's one of the shunts is on the back of the card. And we have 2 of those chips because there's also other shunt resistors that need to be monitored. Like, I'm pretty sure that those are shunt resistors as well that are also being monitored. And the reason why we have all of this new monitoring circuitry on these cards is because NVIDIA has per power connector based power limits. And that means you need to actually balance your power connectors if you don't want to bounce off the power limit all of the time, which is something they've sort of improved from the 10 series. Now, if you're wondering if AMD has this circuitry, AMD doesn't have this circuitry because AMD doesn't bother to actually monitor how much current is going into the card. They just care how much current is going through the VRM. And that's really the only thing they monitor. And more interestingly, they only monitor the power consumption for like VCore on most cards, and on some cards they'll also include the memory power. But the memory controller, because AMD has a separate memory controller rail, they don't bother with that one. That one's static. That one's not monitored. So yeah, that's kind of an interesting thing to consider. Ultimately, NVIDIA, has all this extra current monitoring and current balancing circuitry just kind of because they're really focused on power efficiency, I guess. But it does really up the complexity of the cards, which is why we have 2 NCP 45491s. Like, each of these can monitor 4 shunts. So yeah, there's a lot of current monitoring going on these cards. The other thing we have all over the place is a whole bunch of like these random, well, they seem relatively randomly placed MOSFETs, and those are used for current balancing along with like these inductors right here. So we have another one of those circuits down here, and that is taken care of by UPI Semiconductor UP76561 chips. And those just basically choose which power connector to hook up to which like they're gonna change the power connector that certain phases are pulling their power from based on how much power is being pulled through each power connector. So it's gonna optimize that you like never exceed the 75 watt limit of the PCIe slot, never exceed the 150 or like whatever power limit it is that the 8 pins each have. So yeah, they can current balance all of those so that you never, so that you max out your power allowance, because ultimately you're still going to power throttle at some point, but it's going to reduce the amount of power throttling happening otherwise, compared to what like the 10 series cards would do. So that's pretty neat, and I've already talked about the sort of interesting phases on either side of the GPU core layout in past videos. So if you want to, find out about that, you can watch those. And for the and for the shunt resistors, I've actually done a video about how to mod these like really advanced, where you can completely disable the power limit. I'm not talking like change the power limit by a couple percent. I mean no power limit whatsoever. So I've done another video on that as well, and I'm not going to include that because that takes a while to explain. So yeah, that is the RTX 2080 Ti FTW3 from EVGA. It's a pretty, I hate to say it, but it's basically a bog standard custom RTX 2080 Ti as far as I'm concerned. The inclusion of the BIOS switch is nice. I do really I do appreciate that quite a bit, but ultimately it's really not that different from all of the other RTX 2080 Ti's out there. The VRM is basically the same efficiency as everybody else. The phase count is the same as everybody else. The power balancing is the same as everyone except MSI, who somehow seems to have gotten away with eliminating a bunch of it. But I guess that's because they do have the extra 6-pin. So yeah, that is the FTW3. It's really good. It's just not anything special because this is kind of standard for RTX 2080 Ti's. But yeah, so that is it for the video. Thank you for watching. Like, share, subscribe if you'd like to support Gamers Nexus. There's store.gamersnexus.net, where you can pick up things like the mod mat that you can see in the background of the video here, and also shirts and mugs and other kinds of merch. And then what else is there? We also have a Patreon, so if you'd like to support us through that, you can. There's going to be links to all of that somewhere below the video description or comments as well. And if you'd like to see more overclocking related content, I have a channel called Actually Hardcore Overclocking, where I do things like explain how to do proper shunt mods, not just liquid metal or something like that. There's a better way to completely disable the power limit. And also mods for the things like the UP9512. So if you'd like to check that out, that would be pretty neat. And that is it. So goodbye.